Alyssa. And
hello.
And
hello. Are you saying hello?
Carrie,
Adele?
and Carrie.
And Carrie.
Oh yeah. So many people.
I love Carrie.
Sean, they're all saying hi. Okay, and we know you're here for your game. So Pat, order is important in Jesse's. Why was the order important in this example besides the fact that they said permutations? Whenever you are arranging letters, what do you have to think of them as? Words. And words, C-A-T, is different than T-A-C. Now, hold on. Is A and B and B and A actual words with friends words that they would count? Probably not. But we have to think about them as the order is important if we're trying to think of arrangements. In a song, if you have a C and then an E or an E and then a C, is that a different arrangement? Yes. True? In a class, if you have, let's see, another way of putting this. A president being one person and the secretary being another person, or the roles are flipped, theoretically, would you have different decisions coming out of that student council? Probably yes.
Is this 6 factorial?
Right? So whenever order is important, not 6 factorial, but it's a piece of it. What piece of 6 factorial is this one? For this one where order is important, we were able to use fundamental counting principle and we were able to say how many letters for the first, how many letters for the second, how many letters are possible for the third.
Oh, wait, why do we have only 3 slots?
Ooh, how come? I honestly don't know. I was thinking of another example where they asked for how many 3 letter permutations. Apologize. Only how many 3 letter permutations? Why don't you go ahead and change the example just because we wrote down that answer yesterday. How many 3 letter permutations? How many 3 letter permutations? So what if you were trying to fit in only 3 letters on the Scrabble board and you had these 6 letters to choose from? That's how I said it yesterday, just it wasn't written that way. So for the first letter you have 6 different options, second letter 5 different, third letter 4 different options. Now, if we're choosing a 3-letter permutation, actually, do you guys know what should have gone here instead? How many letters do you have total? 6. How many are you choosing? 3 of them. What must then a permutation formula do? How could you get 6, 5, 4 left over? What if we start with 6 factorial? What would we have to divide by in order to get the rest of this stuff? Yeah, we would need to cancel out the 3 and the 2 and the 1, so we would need to have 3 factorial. Question, do you guys see from NPR up above, from 6P3, how we could get 3 factorial? No? Okay, I'll show it. 6 factorial over 6 minus 3 factorial. Kind of working backwards to the formula for 6P3. And that would end up equaling 4 times 5 is 20.
Factorial, R factorial?
120 different possible permutations. Careful. We're going to have to talk about the word combination and how it's much overused or wrongly used, mathematically speaking, in our culture. Okay. Yeah.
Why isn't there another 3 factorial?
Because it isn't NCR, it's NPR, so we're seeing it that it's going to be solved a little bit differently. Does that make sense?
Just the letter?
Yeah, the letter's going to make the difference. We're actually going to talk about it on the next page, so let's get there so we can write it down. How is NPR different than NCR? If you have a certain number of elements, and we'll say n, like on the page before, if you have a certain number of elements, and you're using all of them, the number of ways all of those elements could be reordered. If we were using every single one of them, you would just end up with the first position, you have n, second position, you have n minus 1, and we keep on going all the way down, so you could just say n factorial. Another way of saying it is that you could go ahead and put it in parentheses and say n, p, n. From n objects you are taking or choosing or using all n of them. But as soon as you have a total number of elements and you're only taking some of them, you're only using some of them, like the example on the last page, there were 6 total letters and we were only using 3. Then it's a little bit more complicated than just n factorial because not all the blanks are filled, so we only go down to a certain place and then stop. And that is where NPR comes in, or is super necessary. And this is the formula that Luca said a second ago, and as Kristen mentioned, it looks an awful lot like NCR. But what is missing? Yeah, the other R factorial. So NPR and NCR are super, super, super similar, but NPR actually has more options. And that kind of comes back to that example we were doing the other day with the computer and the generating of the integers. We were like, hey, there are 4 different ways this could happen, or at least 4 different combinations of numbers. I think it was 1 and 8, 2 and 7, 3 and 6, and 4 and 5. There were 4 different groups of numbers that would accomplish what we wanted it to be, but there were 8 different orders, 8 total different ways of how those numbers could appear. So permutations, the number is always bigger, and if the number is bigger, then we're not dividing by as much. And we'll try to show that, illustrate that today. Just a little bit. Once you guys finish the box, look at that example down below. Having to do with batting orders this time. Question, can a batting order make or break a game?
Sure.
So is the order important? Yes. However, do all the players necessarily get into the batting order for a particular inning? No. In this particular example, the baseball coach is creating a 9-player batting order, but his entire team is how many players? 15. So question, we already talked about how order is important. Could we use the fundamental counting principle, 1, 2, 3, 4, 5, 6, 7, 8, 9? Could we use the fundamental counting principle to say, hey, he's choosing 9 different spots, the first and the second and the third and the fourth? Could we use that? The answer is yeah. How many players does he have to choose from for the first? 15 players. How about for the next? How about for the next? Okay. Dot, dot, dot. When am I going to end? So I have 12, I have 11, I have 10, I have 9, I have 8. Not all the players get used though, right? But who wants to put that in their calculator, honestly? Nobody, so use your factorial knowledge. Just make sure we're not looking at our phones. And what do we get instead? Not instead. What's another way of representing this? 15 factorial, but take away what part? Who's missing? 6 factorial is missing. 6, 5, 4, 3, 2, 1 is missing. And what is this the exact same thing as? Careful. Look back at the problem. We can make this a permutation. We had 15, and how many are we choosing? Good. Where's the 6 come from? What's 15 minus 9? Got it. That's how the formula works. So here's the idea. Maybe permutation would just come up with, because it's like, that's annoying to plug in. That's still kind of annoying to plug in. Hey, let's make a little computer function and call it permutation. Where is that in your calculator? Math. Go over to prob. Probability. NPR. But when you use the NPR, remember, don't you have to type in the number first and then NPR and then the second number? If you forget it, can you do a little like second insert sort of thingamabob? And what do you guys get when you solve?
So wrong number.
Double check me. Did I get all the numbers in there? Oops, sorry, I'm zoomed in. There you go. Ooh. I'd say the coach has some options, huh? Now, of course, there are lots of different things that could come into play as to why he wouldn't make most of those choices, but still, those are all the different ways of ordering. Once again, why are we using this thing called permutation? Why don't we just like find all the possible ones and count them up? No. Okay, so that's one. I think that's the second hint that we've had, right? We had fundamental counting principle, the idea of you can make the blanks for the separate events if they're all happening in sequence, if you're choosing a first and a second and a third of something, for a license plate, for a phone number, for a batting order, for a word, forming a word. Then we talked about permutations, like, hey, if order matters, maybe we can simplify the whole making the blanks and filling the numbers thingamabob. There's something else we gotta talk about, repeated objects. They make things a little bit more complicated. If you reach into a Scrabble bag, and you reach out, or you find like that you have 3 B's and 4 T's, 5 T's. Do you have as many options as the number of letters would seem to indicate? The formula I think is kind of complicated, so I'm going to try and explain it as best as possible. If I were you, I would put a little star by repeated objects just because the best way to learn him, I think, is using the examples. The best way to learn how to do him is using the examples. If I was to give you a whole paragraph as to how this thing works, it's kind of complicated. But if you notice, you do have your big ol' n factorial up top. And we're assuming that we're using all the letters. That's why it's just n factorial. There's no like NPR up there. But there still is something going on down here in the denominator. It's not for the R. I'm not like only choosing some of the letters. So what is it for? Here's my illustration. I'm going to zoom in real quick. My illustration. How many different possible ways are there of ordering A and B and C? 6. You choose 3 and then 2 and then 1. And if we wanted to be really specific, couldn't we, because it's kind of easy, couldn't we list the 6 to be okay? A, B, C. We could do A, C, B. We could do B, A, C. We could do B, C, A. You guys see my pattern? I'm just doing the 2 A ones and the 2 B ones, and what will come next?
The 2 ones.
The 2 C ones. Hey, look, there are 6 of them, and that's it. So what would change if I were to ask you, okay, that's cool, there's 6 different options for A, B, C, which would be the same as 3 times 2 times 1, or 3 factorial. What if I do this one and say, okay, how many different orderings are there of A and B? Okay, let's do the same system. A, B, A, B, A. Different letter tile, but the question, would it be a different arrangement if we were to do the exact same thing with the other A? We could do AAB, right, for the second A, and ABA. Here's the dealio. There's no like color distinguishing between them, and then we go on and we do our BAA. Uh-oh, struggle. BAA. Which of these are repeats as far as the arrangement and what it makes? He's a repeat. He's a repeat, he's a repeat, right? How many options are there total? Only 3. What decreased how many options or orders there are? The repeated object, the repeated letter. So, because of that, we kind of have to think about it as, okay, well, wait a minute, how can we go from 6 down to 3? Well, we can cut in 2, we can divide, right? And here's how we do it. For A, B, C, we could find a number by going ahead and saying, oh, no big deal, there's going to be 3 factorial different options, right? 3 times 2 times 1. For the second one, we can say, yeah, 3 factorial, there are 3 objects, but oh no, there are 2 A's. See it? What's that going to do? What's 3 times 2 times 1? 6. What's 2 times 1? 2. How many are left? 3. And that gets me to my 3 options. So let's try to use this idea of whenever we have repeated objects, for each repeated object, we need to divide by how many times it's repeated.
So 44, would it be divided by 3 factorial, 5 factorial?
Well, hold on, let's start with the total number of objects. Let's start with the top. Different arrangements. We're saying that we have 1, 2, 3. How many letters do we have? 8? Okay. Let's say we're doing technically 8p8. Out of 8 objects, we're choosing all 8, which is going to end up just being 8 factorial. Plug in the formula, just trust me, it's 8 factorial. 8 letters, we're choosing all 8. But, oh my goodness, look at all the repeats, guys. In order to actually solve, we choose that 8 factorial, but we have to divide by, well, okay, who's being repeated? The B's and the T's. But look up above, I separate the repeated objects. So if I separate, well, how many times is B repeated? The answer is 3. How many times is T repeated? And the answer is, that's how I solve. I say divide by 3 factorial for all the different ways that theoretically these 3 could be rearranged that won't result in any difference. And then divide by 5 factorial, the 5 factorial different ways all those T's could be arranged that don't make a difference. And if you guys are trying to have fun with factorials and not just plugging it into your calculator, calculatrice, calculadora, aka, I shouldn't say aka, PS. Is our NPR gonna totally solve this for us? No, it only gets to the very top, right? It only gets this portion. I'm gonna get 8 times 7 times 6, all over 3 times 2 times 1. Hey, nice, 3 times 2 is 6. Therefore, I get 56 different possible arrangements of those 6 letters. Now, if the SAT starts saying there's a blue B and a red B and a yellow B, well then that's a little bit more complicated because aren't they different B's then? Does that make sense? If we just had 3 B Scrabble letter tiles, if you rearrange all the B's, it's not a new letter or word. I should say, it's not a new word. So you guys, set up number 45 if you haven't yet. What would you do with algebra? Should have Mississippi. Just kidding, that's in homework. By 20?
Yeah.
If you're going to your calculator anyway, because you've gone and found your little factorials, yeah. This one wasn't quite so nice to do by hand.
It's from the 5 T's.
Y divided by 2, how many A's are there? Now question. Good. Why or how would it change if I was to say, using the letters in algebra, how many 3-letter words could you make? What changes? Yeah, what do do you change, or how do you change the NPR? Good. You would still divide by the 2 factorial because you have 2 A's, but instead of just doing 7 factorial on top, you have to say, uh-oh, I have 7, but I'm only choosing 3 of them. Does that make sense? That's how you would apply this idea of a repeated object, how you need to divide by how many repeats. You still have the repeated A's, you still divide by that. But instead of just having the 7 factorial, which is if we have all 7 letters and we're using all 7, we have to say, oh, we have all 7, but we're only using 3. Is that okay?
How are we finding this without the calculator? The 7p3?
Oh, then we'd have to go ahead and use our formula from the page before. So we'd have our 7 factorial all over 7 minus 3, which is 4 factorial, all over 2 factorial. And if you want, you could end up doing the snazzy, move it to the top to make it make more sense, like if you want to make it look pretty. So your final expression that you'd be solving would be 7 factorial all over 4 factorial, 2 factorial. Struggle. Styluses sometimes work and sometimes don't. Mental mathers, anybody got there yet?
Oh, you only have 3 slots.
That'd be 765 divided by 2. 1 and 3. 35 and 3. Is that 105? 765, 4 factorial cancels. All over 2. 2 and 6 is 1 and 3. 3 and 35. Got it. Now. What's the difference between permutations and combinations? Oh, look!
Matters.
One little dude came back. Look at him. There he is. But in different contexts, it's being applied not to binomial theorem and coefficients of expanded polynomials, but now he's being applied to how many different groupings are possible. Not arrangements, but groupings. Not arrangements, but groupings. AKA, order is not important. Order does not matter. I have an illustration to help us with this, but I'll wait till you guys get the formulas down. Number 1, to remind yourselves of who NCR is, and technically to tell us where NCR comes from. Because NCR says, cool, NPR different arrangements, but guess what? All the reorderings of the exact same grouping, I don't care about. Let's divide by R factorial. NCR says, NPR different arrangements, cool, but some of those are the exact same key components, just rearranged. I don't care about those. I'll divide by R factorial. Ready for my example before we get to the problem down below? You work at a pizza place. Let's do a mom and pop one, not like one of the big chains. Working in the back. 2 different people order the exact same pizza. Or is it? They order, what should we put on it? Mushrooms? Okay.
Ew.
That's okay. Mushrooms, and we gotta get a protein in there.
Chicken.
And
Barbecue chicken.
anyway, okay, let's not make it too crazy. Let's do mushrooms, and then I heard sausage, and then I heard pepperoni, and then chicken. Okay. So we'll say, that's a weird combination. Let's look up chicken. Okay, so pepperoni, sausage, and then mushrooms. We'll do that. Pepperoni, sausage, and then mushrooms. Okay, let's say you're working in the back, and you get 2 exact same orders for pepperoni. Well, hold on. One of them orders pepperoni, sausage, mushrooms, and the other one orders mushrooms, pepperoni, sausage. You're going fast, and so you go ahead and put the toppings on in the exact same order as it was called out or written to you? Question. Are they two different pizzas?
No.
No. Unless you want to be like,
It's the
nah,
same to me.
they're two different permutations. You're like, nah. But anyone in the front would be like, oh, hey, we need two of the same order, right? Why? It's a combo pizza. Who cares? Oh, it's a combo pizza. Who cares what order the toppings get put on as long as they get put on, right? Okay. That is one sense where combination is used mathematically correctly? Mathematically accurate. It's accurate mathematically done. Okay, question. Where is a place where combination is used incorrectly in a mathematical sense? Think about the hallway. Why? They're supposed to be called Hopper permutations? Whoa. So if they want your combo, say, you need my perm? Anyway, so. Combo pizzas, that's an accurate way.
Phone numbers.
Phone numbers, that would be a permutation, right? But someone could say, hey, what's the combination of your number? What's your address combo? Anyway, lockers, should be a permutation. Pizzas, okay, we'll take a combo. Sound good? Okay. Question, why is this example a combination and not a permutation? It's a committee, right? Who cares what order you put their names? Well, I guess someone out there would probably care. Either way. Who cares what order they were chosen? Someone out there would probably care. But question is, will it be the same committee if the admin walks in first, and then the three faculty members, and then the two students, or then the two students and the three faculty members? Ooh, what if the faculty members change it up if one comes in before? It doesn't matter. It's the same committee that's there, right? Okay. Forming a committee, if there is no position titles given, because a committee with a student as president would be very different than a committee with an admin as president, right? Unless the student has to follow the admin, but that would be the president. So anyway, coming back. If there are positions given, then it's a permutation, because then things can change. However, if it's just a committee, if it's just a group, we say combination. So, kiddos, hold on, check out the example. We know to use NCR somehow, but we have a lot going on in this example, right? I've underlined already the main parts of, we need one admin, true? So we'll say admin. We'll say three events. We're choosing the admin. How many different ways the admin can be chosen? How many different ways the faculty members can be chosen? And then how many different ways the students can be chosen? But just how they can be chosen. We don't care about whether student 1 is listed first, then student 2, or whatever. So we need to choose admin, faculty, and students. Now, there's still choices being made, but the arrangement doesn't matter. So we're using NCR instead of NPR. Question, how many different ways can we, just give me an expression, not the number, how many different ways can the admin be chosen? 7. There's 7 admin, and we're choosing 1. Now, some of you are like, oh, wait a minute, 7 choosing 1. Is that going to just end up being 7? And you're right. However, if we're trying to do combination, and this is why I'm trying to do combination, how about the next one? There's 12, right? And out of the 12, you're choosing 3. Does that make sense? We wouldn't want to come up with the number ourselves in there. We'll just use combinations to help us out. How about students? What are we going to do? So can you in your calculator do multiple combinations multiply together? Of course you can. We go ahead and say, oh, no, we're going to try it. Go try it. Math prob. If you accidentally put the NCR before you put the 7, just go back, second insert. Put the 7 in first. But check it out. You can do one NCR, then do it times, another NCR, then times, another NCR, and then do enter. Did it work?
Yeah.
Go team. Let's see if we all got the right answer. What did you get?
292,600.
Say it one more time.
292,600.
I heard a couple of yes. So those are the different possible combination of committees, combinations of committees.
A1.
So then if I was talking about a pizza place, and if I was talking about, hey, they have 25 different ingredients, how many different 3-topping pizzas could you possibly get? What are you going to use? Permutation or combination? Exactly. Does that make sense? Oh my goodness, we're done. Go team. Kiddos, what kind of numbers are you going to have in this homework? There's 292,600, 2,520, 56, 105. Are these like little decimals or are they big numbers? Some are cute and some are just kind of big. What's different from section 9.7?
Because they're coming back to me.
Fractions.
My husband's
Fractions. Now kiddos, we do need to start 9.7, so we're going to do that, but I do have a homework help first. And then we'll do, let's skip this page. I'm going to talk about it tomorrow after the homework. So you guys start looking for homework help as I take things. Okay, go quick. Let's see how well you have the idea of 9.6 before we quickly go into 9.7, which says, figure out how many ways this is possible over how many total ways, and figure out the likelihood or the chances or the percent probability. Still 9.6. Still trying to figure out how many. Possibly big numbers. What do we got, kiddos?
Ooh.
Just got more comes.
25, 292.
All good units. So we need to kind of take this information and say, okay, if there are 25 total, what does that 25 total break up into? 3 bad or defective? 22 good. So careful, they might not give you all the information at once. Does that make sense? Okay, so all good units. Out of 25, you're right. Why C and not P? Yeah, it doesn't matter what order you open the boxes. You just care about what you have that work or don't work. Wait, hold on. But they're not purchasing 22, guys. They're purchasing 4. Oh, and how many of them are good that we want the 4 out of?
1.
There you go. Does that make sense?
Oh, look at this thing.
We're not caring about, that's why it says C and not a P. We're not caring about whether these 4 TVs that come out that are all good, if we get them, like open up this one first and then that one. We don't care about the opening. We don't care about the order of opening. But there are 22 different good ones, and we're saying how many ways can you get 4 that are good from those 22. Let's not solve that. Let's just go on to the next one. How many ways could they receive 2 good units?
Can you make a ratio?
Not a ratio yet. We're not asking about chances. Not the probability, just how many ways. Okay, so they did get 2 good units. So out of the 22, they're getting 2 good ones. But why am I saying an and?
Because you also got a bad one.
They're getting 4 total. So that's how to get the 2 good. But if they have 2 good, then they must have
Maybe.
2 bad. So out of the bad ones, does that make sense? They're getting 2 good ones and, fundamental accounting principle doesn't just work for permutations. They're getting 2 good ones and 2 bad ones.
I have no idea for letter C though.
Letter C gets harder because it says at least 2. So it's not exactly 2. So wait. From letter C, could we still say that 2 good units is an option to meet this condition?
Yeah.
So we can say 22C2 and 3C2. That's one option. Or, not 22C2, 22C1, that would be only one good unit.
Right.
We could get 3 good units, at least 2. 3 good units and how many bad units?
1.
Okay, so then 3C1. Is there another or?
22C4.
22C4. And how many bad units? Oh wait, that'd be none, because all 4 are. Now question, in math, what do you think or is? Either of them are good options, that's good. What operation could we put in there? And says, okay, I'll take each of these and then I'll go ahead and put with each one all the different options again and again and again and again. You're multiplying. Or, not equal, that'd be more like an is. Or. If I have 5 apples up here and if I have 2 oranges, you can say, hey, you can have an apple or an orange. How many options do you have to choose from?
2.
You add them up, right? If I have 5 apples, 2 oranges, you can have an apple or an orange. You come up, how many do you have to choose from? Oh, whatever, I can have an apple or an orange. I put them all together and say, hey, I have 7 options. Same thing in math. Replace the or with a, just add them all together. Just add them all together. And means multiply with probability, or means addition. Almost always. And means multiply, or means addition. So, what words can get kind of tricky with probability or with the idea of probability? At least, at most, because then you have multiple options of how it could be true. Just watch out for them, and I'm sure we're going to see them in section 9.7. Speaking of, let's start. 9.6, big numbers. How many ways possible? 9.7. How many ways possible for something special to happen out of how many ways total? What are the chances? Small numbers, decimals to be precise. Here's your ratio, Luca. Probability. The chances of a favorable outcome actually occurring. I'm filling in a couple things real quick to help us with the formula below. Outcomes. How many ways something can happen. They're going to show that with n. So that kind of comes from section 9.6. So as you guys do 9.6, just think about you're kind of learning how to do the first half of 9.7. Sometimes in probability, they make us come up with the numbers ourselves, and sometimes they give us like the actual chances or the percentages, and we have to learn how to work with them. So there are 2 different ways of doing probability. One is to find it yourself, and one is to work with the chances they're telling you. Sample space, that's going to be S. That's going to be the total outcomes. Favorable and not favorable or non-favorable. The sample space is just like, hey, what are all the different ways that this could happen, not just the ones that meet this special favorable outcome. And favorable outcome is where that little e comes from below, which is the event. The only, I think, variable we haven't defined from down below is p. And p just stands for probability. Not property. So So long story short, probability of something occurring, probability of, that's function notation, probability of an event occurring is the number of ways the event can occur over just the total number of ways of the sample space, aka the number of favorable outcomes over the total number of outcomes, favorable and non-favorable put together. So what are the chances that you would get heads? I asked yesterday how many different ways can you flip a coin, and you guys said 2. Meaning, how many different ways, can a coin land? And assuming it lands on a side, we'll say 2, heads or tails. And now I say, what are the chances out of one coin flip of you getting heads? You would say, oh, 1 out of those 2 would meet that condition. Does that make sense? So your chances would be 1/2, or what percentage? 50%. But what if I was to say, hey, you flipped the coin twice. Now what are your chances of getting at least 1 head? That's what 9-7 gets into. How close are we? Oh, we're so close. So we'll just get down these 2 special probabilities, and tomorrow we'll start dealing with the more complicated things that might occur. If the probability of something occurring is 0, we say E is an impossible event. And why is it impossible? Its chances are 0. It's not going to happen, right? It's not even like 1 in a million. It's just like not at all. So if the probability is ever 0, then we can say E cannot occur, so E is an impossible event. And if the probability is 1, oh, that's so little, that's so small. Wait a minute. Why am I saying that the event must occur, aka that E is a guaranteed or a certain event? Wait a minute, kiddos, 1 is so tiny compared to all the numbers in section 9.6. I don't get it. Why does the probability of 1 mean it must occur? What's 1? 1.00 or 100%. Ah! Homework tonight! Yeah, big numbers! Homework in 9-7? Oh, we're going to have little baby ones. Bye, guys. Happy nutrition on a Wednesday. If you see Sean, tell me missed him. And Carrie, and Alyssa. I don't know if they're coming.
Oh, yeah.
I thought I saw Carrie.
Yeah, let me stop it.